Next, we turn our attention to factoring trinomials in general. Now, we already know how to factor quadratic trinomials. When we want to factor just any random trinomial of degree usually higher than 2, we're going to try to pretend that it's quadratic. And this is a technique that we're going to use with polynomials pretty frequently, actually, is essentially pretending we have a nicer polynomial than we do. Formally, something like this is called quadratic in form. But what we mean is it's something we can pretend is quadratic. So how do we factor this? Well, first we factor out the greatest common factor. And we're going to notice that this term has no variable factor. So there's no variable common factor. But now looking at each of these numbers, we spot that each of these is a multiple of 5. So our greatest common factor is going to be 5. When we factor that out, we'll have 10x to the 4th divided by 5 is 2x to the 4th. Negative 25x squared divided by 5 is negative 5x squared. Negative 60 divided by 5 is negative 12. And now we have our greatest common factor factored out. And what remains is to factor 2x to the 4th minus 5x squared minus 12. We're going to notice that that's 2 times x squared squared minus 5 times x squared minus 12. And what we're going to think is, okay, imagine I'm putting both of those x squareds in a box of some kind. Imagine sealing up this x squared. If I do that, then what I have is a quadratic polynomial. It just happens to be quadratic in x squared instead of in x. What's the point? Well, I can use the AC method when the variable in one term is the square of the variable in another. I can say AC is 2 times negative 12 is negative 24, and B is negative 5. So I need to find two numbers that multiply to give me negative 24 and add up to give me negative 5. And a little bit of trial and error tells me that 3 times negative 8 gives me negative 24. 3 plus negative 8 is negative 5. Now my leading coefficient here is not 1, so the two numbers that show up in the AC method will not be the numbers that show up in the factors. But I can factor by splitting up that middle term. We'll set up a rectangle to use to factor, and we'll start by filling in our 2x to the 4th and our negative 12. And then we're splitting up that middle term as a negative 8x squared plus a positive 3x squared. Okay, now we look at the first row, and we see that the greatest common factor in the first row is a 2x squared. 2x squared times what gives us 2x to the 4th? That's going to be an x squared. 2x squared times what gives us negative 8x squared? That's going to be a negative 4. X squared times what gives us a positive 3x squared? That's going to be a positive 3. And finally, we check. Positive 3 times negative 4, does that give us a negative 12? It does. So, we've factored our trinomial here as the product 2x squared plus 3 down the side times x squared minus 4 across the top. 2x squared plus 3, that has two terms. I can factor it if it's a special form, but that's definitely not a special form. Right, I have an x squared, so my only hope would be a difference of squares. But that's addition. Neither term is a perfect square. This is prime. What about my other factor? I have x squared minus 4. Two terms again, so I'll look for special forms. But I think that 4 is a perfect square. So x squared minus 4, that's x squared minus 2 squared. So that'll be x minus 2 times x plus 2. And now these guys are linear, so they're prime. Once I'm down to linear stuff, I know I can stop. So I've factored this factor, discovered this one was prime. I've gotten everything as factored as I can. Now I just need to put it all together. I have my GCF of 5 times 2x squared plus 3 times x minus 2 times x plus 2. And now that's my trinomial, which is higher degree than quadratic, but I could pretend. That's my trinomial, fully factored.